Hi to all. Today I am going to explain some important points. The fringe width in Young's interference experiment. What is fringe width? In the previous lecture, I derived the fringe width formula, right? The fringe width is nothing but it is the distance between the successive bright bands. You see the figure, this is a bright band. Okay, in these lines are there is a bright band. This is the center of the bright band. This is the another bright band. Its center is this one, black line. The distance between the two successive bright bands is called as the fringe width, or it may be taken as the distance between the successive bright bands or successive dark bands also you can take. Okay, the fringe width is nothing but distance between the between distance between successive successive bright bands or dark bands is called as fringe width. We derived the fringe width formula, that is lambda into capital D by small d. This is the formula. Okay. In this, lambda is the wavelength of the light. Fringe width depends upon the wavelength of light, and capital D is the distance of screen from slits. Small d is the distance between two slits. Distance between two slits. You know very well. And now beta proportional to lambda from this, and beta proportional to capital D, and beta inversely proportional to small d. For example, how we can increase the beta? For example, if lambda increases, what happens? Beta increases because they are directly proportional. Is that right? If capital D increases, then also beta increases. Fringe width increases, band width increases means bands appears clearly. Okay, in order to apply to get the clear bandwidth, to be clear bands, then we have to increase the fringe width. Then if small the separation between the slits is decreased, then also fringe width will be increases. In order to increase the fringe width, what we have to do? We have to increase the wavelength, increase the d and decrease the small d. Why we have to decrease the small d? Because beta is inversely proportional to small d from this. Okay, beta is inversely proportional to small d. When the small d decreases, beta increases. Capital D increases, beta increases because they are directly proportional. Okay, and the next one is how this fringe width will be affect when we dip in the liquid. Okay, and before that, we are going to I'm going to explain one thing, that is angular fringe width. That our next topic is angular fringe width. Angular fringe width. What is angular fringe width? Angular fringe width is nothing but one fringe width. How much angle it makes at the center of the screen. That is the angular fringe width. We will draw the diagram it here. This is the source, and now this is Young's double slit experiment actually. It's an Young's double slit experiment. Young's double slit experiment for what purpose? It is interference. Interference of light. Interference is nothing but superposition of two light waves. Due to that, redistribution of light energy takes place. This is the slits S1 and S2. Okay, and S is the source, and this is the screen, right? See the figure very carefully. And this is the center of the screen. O is the center of the screen. And here bright band, dark bands will be forms. And if you take any light ray here, the light ray started from the source S, and they will incident on the two slits. Slits is nothing but openings through that light passes, and that light is incidenting on the screen at here like this. And at every point on the screen, the letters will be meet, and this is a point P. And here, what I want to do it here, for example, this is the bright band, okay, and this is the dark band. And for example, this is the center bright band. You know, center bright band will forms, right? This is the bright band. This is also bright band, and in the middle, dark band is there. Okay, you see here very carefully. And this is the bright band, bright. This is the dark. This is the bright. And now this is the beta, right? This is beta. The distance between the successive bright bands is called as the fringe width. You join the center of the midpoint of two slits with the fringe width. Okay, this is making some angle at here. Very simple here. I will draw the radiator diagram. And for example, this is the fringe width. Okay, fringe width is beta. And this fringe width is making some angle at here, right? At the slit. And this distance is capital D. We know that this distance. This is O dash. Actually, this is O, and this is P from the figure. Okay, you see here, there is an O dash P O, right? The fringe width is making some angle at here. This is the fringe width. It is making at some angle. Okay, that angle is called as angular fringe width. An angular fringe width is it is the theta. We write nearly theta is nearly equal to tan theta. We write when theta is small. Tan theta from the figure we write as beta by capital D. Then but beta is equal to, we know that lambda into capital D by small d by capital D. This capital D will be cancelled. Then angular fringe width formula we will get as angular fringe width we will get as angular fringe width is theta. Theta is equal to, we will get as lambda by small d. Okay, this is the formula for the angular fringe width. Okay, angular fringe width is in radians. Now angular lambda is the wavelength here. Okay, and d is already, we know that distance between the two slits. Okay, and now from above equation, okay, we write one sentence that is fringe width depends upon distance of screen also. But here from above formula, angular fringe width is independent of distance of screen from slits. From the figure we are seeing this angular fringe width. Angular fringe width does not depends upon the capital D. Capital D is the distance of the screen from the slits. The fringe width depends upon the capital D, but angular fringe width does not depends upon the capital D. Next, when we dip this Young's double slit experiment, okay, in a liquid of refractive index nu, then what happens? Okay, you take the screenshot and note it. I am going to rub. some important point I'm going to do in the note. If Young's double slit experiment, Young's double slit experiment is dip in the liquid of refractive index nu, then fringe width, and angular fringe width and angular fringe width decreases. Fringe width becomes 1 by nu times of its value in air. What I am doing it here, if we dip the Young's double slit experiment in the liquid, then what happens to fringe width and what happens to angular fringe width? Fringe width formula in air, okay? Fringe width formula in air, that is lambda in air into capital D by small d. We know the fringe width formula, that is beta is equal to lambda into capital D by small d. From that, fringe width in air formula is this one. If you want the fringe width in liquid, beta in liquid, you will write here wavelength in the liquid into capital D by small d. But there is a relation between the wavelength of light in the liquid and air. That is, when we dip, when the light ray enter into the liquid, its wavelength become 1 by nu times. This we substitute in above equation. Then in liquid we know, right? Beta in liquid is equal to lambda in liquid by air. Lambda in liquid we write as beta in liquid formula from here you see. Lambda in liquid, but lambda in liquid we write here lambda in air by nu into remaining is capital D by small d. From this we write beta in liquid is equal to 1 by nu times of this lambda A in air into capital D by small d. This is beta in liquid is equal to 1 by nu times of beta in air. Okay, means the fringe width become 1 by nu times. Similarly, angular fringe width also. If you write the angular fringe width in the liquid is equal to, we know formula lambda in liquid by nu. Sorry, lambda in liquid by d. Lambda in liquid is lambda in air by nu d. This is lambda in air by d is get 1 by nu into lambda in air by d we write. But the lambda in air by d is angular fringe width in air. Okay, angular fringe width in air by nu. That means what happens to angular fringe width? Angular fringe width also becomes 1 by nu times. Angular fringe width becomes 1 by new times. When we dip the when we dip the Young's double slit experiment in the liquid, then the fringe width and angular fringe width becomes 1 by nu times. Take the screenshot and note it. Now I am going to give one problem for the homework and you try to solve it yourself and write its solution. Okay. The question is that a simple question. Two coherent sources. Two coherent sources are 0.15 millimeter apart and fringes observed 1 meter away with monochromatic monochromatic light of wavelength 6000 angstroms. Find first fringe width in air. Next, second question, fringe width in liquid of refractive index 5 by 2. This is our question. You try to solve it. What they gave the data I will write. Distance between the two coherent sources are 0.15 millimeter apart. In Young's double slit experiment, there are two coherent sources are there. This is the S1 and S2. Separation between the two slits is the D. The S is the source. And this is the screen you see here. And the distance of the screen from the slits is capital D. This is the center of the screen you see here. This is the center of the screen. From the source light started it here and incident on both the slits. Through the slits light passes and they will superpose. And now this point O P, this point is O. Let's write the given values what they gave in the question. In the question they gave that two coherent sources. S1 S2 are the coherent sources. Okay, coherent sources. Separation between the coherent sources they give is small d 0.15 millimeter. Convert into meters. 10 to the power of minus 3 meters. Next, fringes are observed with the monochromatic light. Light wavelength they give that they are using 6000 angstroms. 6000 to the power of minus 10 meters. And the fringes are observed at a distance. Here the fringes are observed, right? Here the fringes are observed. The bright, dark, bright, dark, like this. Okay. We will observe the fringes. This is the bright. bright. In the middle, dark will be there. Like this on the screen, we observe the bright and dark bands. This is the center bright. Center we will observe the bright. And now the these fringes are observed at what distance from the slits? That they gave capital D they gave as 1 meter. Then what they are asking in the questions? First fringe width in the air. What is the formula for the fringe width? Lambda capital D by small d. The next question they are asking fringe width in a liquid whose refractive index is nu. Nu is equal to 5 by 2. They are asking the fringe width in the liquid. Yes, you know the fringe width in the liquid formula, fringe width in air formula. Then based on that you solve these problems. Okay. Thank you for watching my lecture.